Moving to the next presentation, we have Team Mother players with us today to present the implementation of maneuver standards since the design. Let's give Team Mother players a round of applause as we welcome them to the stage.
It caused millions of tears, $1,000 of damages, and hundreds of lives. But we only need one small step to change.
Hello marine enthusiasts!
We are Mother's Prayer.
Let's take our part to create a better future for ship's operation.
Honorable Chair, distinguished delegates, ladies and gentlemen. It is such an honor with the deepest gratitude that the Mother's Prayer teams appreciate all of your time to listen to our proposal. Today we are going to present the proposal for the implementation of maneuver standards since the ship design phase. This will be our outline for the presentation today. We will start to discuss the background of our proposal. The second part will be on the problem analysis. After we break down the study case on the third section, we will discuss the proposed solution in the fourth section. And lastly, we will outline the conclusion within our proposal. We will start with the first section of background. From 2019 to 2022, collision has become the main factor in marine accident. It contributes about 27% of total accidents that happen in 2019 to 2022. Ship steering and navigation are growing rapidly, but surprisingly, ship collision as factor of accident are increasingly year by year. On condition analysis that happen, as a ship collision happened due to a maneuver failure, the term of human error is commonly being used in recent decades. The remedial action that takes place is only to give education and training to the seafarer. We believe it is not resolved the main problem where the collision happens, the ship maneuver failure take place. As nowadays the trend goes on to the maritime autonomous surface ship or MAS, it will be likely to happen without the presence of the ship operators. Therefore, maneuverability design standards should be conducted as it leads to a higher demand for ship maneuvering since the ship collision avoidance will rely on the system. This argument has become the main idea to enforce maneuverability standards since the ship design phase. As we could see on the actual condition, IMO also stated that the maneuvering performance still receives a little attention during design stage, as it lacks a standard for regulatory authorities to enforce. This leads to some ship that has been built with poor maneuverability and relied more on operators' navigator. We hope a uniform standards on design stage could be implemented, as it ensures ships are to design not to impose and rely on ship handler abilities. As for the existing standard on MSC 137 and 1053, there is still no exact guidance and criteria standards regarding maneuverability standards. We believe our proposal is in line with IMO's strategic direction from 2018 to 2023. On strategic direction number 1, improve implementation. We hope by introducing the proposal for the implementation of maneuvering standards during the design phase in order to have a uniform standards for understanding maneuverability to minimize maneuverability failure.
Let's move on to the problem analysis. IMO has adopted standards for ship maneuverability. There are 3 main tests required by the standards: turning test, stopping test, and zigzag test. One of the criteria of ship maneuver is turning ability. It is believed in operation that turning ability has become the main criterion that affected the maneuverability of the ship to avoid a collision. It is because the max rudder angle is applied to turn the ship, to their max as possible to avoid a collision. So based on IMC 137 Section 4, the turning circle maneuver is the maneuver to be performed to both starboard and port with a 35-degree rudder angle or the max rudder angle. So based on standards, the advance should not exceed 4.5 ship length and the tactical diameter should not exceed 5 ship length in the turning circle maneuver. In such a case, it will be required to predict the maneuvering performance. As an alternative to scale model test, usually conducted during the ship design phase, a numerical simulation using a mathematical model is a useful method for predicting ship maneuvering performance. But as we can see, based on the standards, the maneuvering assessment at the design stage shows a lack of guidance and information. Following the details, we believe the assessment could be represented in a better flowchart, starting from pre-processing, which consists of data input, followed by simulation, which consists of simulation setup, finalized by post-processing, which consists of criteria check and result plotting.
In this section, we would like to apply our understanding of maneuverability from the design stage. First, we conduct a verification process with our reference model of Moray container ship, or KCS. Let's see what we can get from these hull and rudder characteristics. Here we can see the results. We use a dashed blue line for our simulation, compared to the existing experimental results, which represents by a solid red line. We got differences of 1.1% for advanced and minus 0.63% for tactical diameter, compared to the real experimental results. We will also determine the course keeping ability for our additional requirements, which will be detailed in the next section. In this case, the KCS passed the standards with a positive value of C, which indicates the ships can keep their course steady after experiencing small disturbances. The verification results are satisfactory. Therefore, we applied our analysis to one of the cases of a collided ship. Here we called Jane Doe. We used Jane Doe as our study case because she has similar characteristics compared to the previous case of KCS. Now we can see the results. We represent the simulation results of Jane Doe in a pink dashed dot line, compared to the previous KCS simulation. The results are disappointing, even though it is still accepted by the standards. It failed in course keeping check, which later will be proposed by our team. Let's see the comparison in the next slide. While KCS is having a safety margins of 1.618 and 2.307 ship's length, Jane Doe, with similar characteristics, has relatively low safety margins of 0.018 and 0.708 length for advanced and tactical diameter. With our additional requirements of course keeping ability check, Jane Doe itself failed the requirements. With this study case, we could conclude several outcomes which become our team's urgency to propose amendments to the maneuverability standards. First of all, Jane Doe passed the MSC 137 standards with a relatively low safety margin, but still it is considered to have a good turning circle maneuverability. With our additional requirements, Jane Doe could be considered to have poor turning circle maneuverability, since it failed the course keeping ability and has a relatively low safety margin compared to a similar ship. Therefore, in this case, we believed a better ship's design could be chosen to improve the course keeping ability, while also a better rudder characteristic could be considered to reduce the advanced and tactical diameter. As per our team's proposal, we hope the other poor maneuverability ships could be prevented, resulting in a better future for ships' operation.
In this section, our team will briefly introduce the proposed solution, especially on the policy rules. After understanding the maneuverability assessment in previous case, we summarize the proposed idea into 3 main parts. We believe our proposal could answer those main problems due to maneuver failure that we have breakdown in the study case. MSc 137, Chapter 4, MSc Circular 1053, Chapter 3.3, and Appendix 4 is the main focus of our proposal. As the result has been discussed before, our team believes that the rudder also contributes to the maneuverability design. Hence, we propose on MSc 137, Chapter 4 to have a definition regards the geometry of rudder that includes the head, chord length, and the area of rudder. Next, as stated in MSc 1053, Chapter 3.3, on the mathematical model, on the left box, which is the current rules of IMO, our team proposed adding more detailed guidance to have a uniform standard as it is seen in the right side red color box. In the mathematical model, maneuverability assessment could be done since the basic design phase and applicable to all ships of over 100 meters with rudder as a prime movers. Mathematical models are to be applied in accordance with ship and rudder geometry by using empirical formula which are integrated with numerical simulation to meet the requirement on turning ability, which is stated in MSc 137, Chapter 5.3.1. The result of calculation could be as a preliminary assessment which shall be validated by a model test or full-scale trial as required by the rules. Considering the case of the collided ship Jane Doe, our team believes that course-keeping ability is an important aspect that should be analyzed in the design stage. Hence, our team proposed on Appendix 4 to have a standard criterion on course-keeping with an empirical formula stated in the slide, integrated with the turning ability numerical assessment as a preliminary assessment.
After all the interesting discussions, finally we arrived at the conclusion of this proposal. First of all, the collision has become the main factor in marine accident, and maneuverability still received little attention. This will lead to problems as mass develops with the absence of ship operator who can compensate ship's poor maneuverability. We believed the turning circle maneuver has become one of the criteria of maneuverability, but there is still no specific guidance on design stage, and relies on the full-scale test, which tend to increase the risk of future remedial actions. Therefore, we proposed amendment for Chapter 4 in MSc 137 for definitions, and Chapter 3.3 of MSc Circular 1053 for additional explanations, along with Appendix 4 for additional requirements check of course-keeping ability.
Our team believes everyone could take their part to create a better future for the ship's operation. We hope with this proposal, we could take our part to reduce marine collisions due to the poor maneuverability of ships. Besides, by having a good maneuverability ship, we could reduce fuel consumption due to a better course-keeping ability to support SDG number 7, while also bringing beneficial changes in the way a ship was designed to support SDG number 9. Also reduce production waste produced by remedial actions of maneuverability failure to support SDG number 12. Lastly, we could contribute to safe and environmentally sound marine transportation to support SDG number 14. And these are several references of the study and images that were used in our proposal. Lastly, we would like to finish this presentation with this inspiring quote from the unknown. Prepare and prevent, don't repair and repent. We hope in the future, we won't repent for missing these changes. We won't keep repairing what has been done. and rather start to prepare for even the small changes to prevent any failure that could cost hundreds of lives. Thank you.
Thank you, Team Mothers player, for your interesting presentation. Now, I would like to open the floors first to the judge. Yes, Judge Nam from Kamsa.
Okay, let me ask you one very simple question. And you mentioned in your case study poor maneuverability. Did you find anywhere the definition of the poor maneuverability or criterion for poor maneuverability?
Thank you, judges, for your concern to our proposal. So what we mentioned before in our presentation was poor maneuverability in terms of turning circle. So in this case, we believe with a relatively low safety margin of the similar ships compared to the KCS, and also with our additional requirements of course keeping ability check, can be concluded that the ships have a relatively poor maneuverability with the comparison of the similar ships. Thank you.
Yes, Judge from KR.
Thank you. One more question. Ship speed, ship speed, maneuverability, and those kind of issues is very closely related to the reputation of the shipyard. I mean, my understanding in your slide 28, a lot of collisions are triggered by this poor maneuverability. Do you still in the same position? I mean, when you take a look at the collision issues, most of the cases not related to the hardware. I mean, the human element. It could be one of the reasons, but not so high.
Thank you, judges, for your sincere insights and thoughtful questions. Yes, in many collisions, human error is commonly being used. In here, we are proposed for another preliminary assessment due to a maneuverability. So we hope by our proposal, it could lower the risk of the human error terms in case by having a better understanding maneuverability in the ship, the way the ship designed.
In addition, we also admit that many collision failure happen not only for the reason of poor maneuverability ships, but also considering the hardware failure or the steering system error and several reasons. But as our team's purpose, we hope that we could take our part, even though it's not as a seafarer, but as also a naval architect and designer. So we could create a better future, not only for the seafarers itself, but also for the ship's transportation. Thank you.
Are there any additional comments? Yes, please. Judge Park from KMI.
Thank you for your presentation. And so it's all technical matter. And so I just wondering about the research data, on the basis of your the research data, is your presentation is supply. That is the first question. Another one is you are introduced to the strategic direction. With regard to the strategic direction, number 8, strategic direction. As far as I know, to the IMO don't have to the strategic direction 8. What is the relations to the proposal to the strategic direction 8? That is the second question.
First of all, we would like to apologize. Please, may you repeat the first question because our team still not in the same page.
I mean, my question is your presentation material, your technical data under the graph and the technical data show the graph, and then by carrying out by your the research or to the researchers to the inside.
Thank you for your questions, honorable judges. So for the technical analysis of the simulations, we conducted a simple algorithm with MATLAB software to compare the maneuverability by using the estimation of hydrodynamic coefficients in terms of maneuver. So in academical issues, we only use references as our comparison of the real experimental results because due to the time concern, we cannot do it in our way. So we take references for the final advanced and tactical diameter just for a comparison to our simulations. In this opportunity, we take our understanding and study regards the simulation process by using the hydrodynamic coefficients to understand the correlation between the ship's hull characteristics and also rudder to the final tactical diameter and advance. So by understanding the relation, we could improve or we can know the small changes made in the design phases could lead to a big or small relatively impact to the final maneuverability characteristics, especially in the turning circle.
Yes, thank you. Due to the limited time frame, I'd like to open the floor to the participants of the, yes?
I am sorry. I am sorry, moderator.
Yes.
There is another question by the judge.
Okay, the
Please
second
allow
question,
me
yes.
to
Just
answer
1
it.
minute. Yes, I can give you 1 minute, one more
So-
minutes for that. And then next, yes.
Thank you, honorable judges, for your question. Please allow us to answer on the strategic direction. For the strategic direction number 1 on improved implementation. We hope
I know to the strategic direction, and so you showed to the strategic direction 8. What is the strategic direction 8? According to your slide, show
Yes.
to the strategic direction 8.
yes,
Could you check?
in our proposal, we are in line in strategic direction number 1.
I saw to the strategic direction 8, your slide. Indeed, to the collection. Page 8.
Page 8. Yes, in our PPT, we are stated that the 8th direction is the strategic direction of IMO from 2018 to 2023. But we especially emphasize on the strategic direction number 1 because our proposal is in line with the strategic direction number 1 on improved implementation, judges.
So I would like to recommend to the strategic direction of IMO, from the strategic direction 1. The final is strategic direction 7. There is no strategic direction 8. Could you check it later? Thank you.
All right, judges, thank you for your consideration. We will have a check on it. I am sorry. Thank you.
Thank you, Judge, for your insightful comments. Yes, the last question goes to the methodology. Yes, could you please? Yes.
Thank you, and thank you for a wonderful presentation. And I have a simple question about your case study ship named Jane Doe. I wonder how come did you conclude that the cause of the collision is maneuverability, especially course keeping ability? Can you make it more detailed? Can you tell us more about it? Thank you.
First of all, we would like to thank you for your questions and concerns. So we conclude that Jane Doe is having a poor maneuverability, especially in turning circle and course keeping ability, based on the data that we showed before. So with our simulation, it has similar characteristics compared to the KCS, but we can see the result is disappointing with a relatively low safety margin compared to the similar ships. So the way we conclude poor maneuverability ships is only to give an insight for the designer to improve the maneuverability characteristics of the Jane Doe. So we hope by this opportunity or by this method, we can increase the number of safety in terms of maneuverability. Thank you.
Thank you, Mother's Player, for your participation and presentations for these matters. And please give them a big round of applause.